thanks for coming. I have my slide presentation software is telling me there's like 28 minutes of content, but I have 125 slides, so I'm going to do what I can. We might have to stop early, but you can catch me afterwards. Yeah, there's a lot to get through. Anyway, the slides are all available here. There's a ton of links and a ton of resources. I will show this at the end as well. But if you want to, the thing I use is like, there's a full like responsive slide thing on that at that URL. So if you want to follow along, you can do that. But like I said, I'll show it again earlier. There might be some things you want to link to and everything. I've done my best to provide URLs to everything. So if you want to do more research afterwards, by all means. So yeah, let's get going. N'hésitez pas à poser vos questions ou demander de la clarification en français. Je trouve qu'il manque de talk technique en français, mais moi je vis dans un monde anglais et tout ce vocabulaire-là, je ne le connais pas. Mais pendant la présentation, si jamais vous voulez une clarification, il y a quelque chose qui n'est pas clair, n'hésitez pas à me demander, je suis très content de me clarifier. Sinon, ça aurait pris 2 fois plus longtemps de créer la présentation, donc je fais ce que je peux. All right. So yeah, to give you a bit of context as to why I'm giving this talk, there's a pattern that I've seen a lot in a lot of like database apps that I've worked on, and to illustrate that, let's build a to-do app. Yay! So you put on your product management hat and you start throwing some killer user stories into Jira. And so we got users can create to-dos. Woo! And so as if in a trance, your fingers start typing out the language of our forefathers. Create table, insert some to-dos, and then we can see a list of their to-dos. Okay, we'll do a select and we'll add a where. And I can view a single to-do. Same thing, but now I have an ID. All this is CRUD. We've seen this before. Welcome to software engineering. It's mostly about recreating Microsoft Access and concatenating strings. Of course, unless, of course, you're an engineer at Wunderlist in the mid-2010s, in which case to-dos are your Everest. But we're not ready for our SoftBank round yet, so we're going to add more features. So users can filter to-dos based on when they were created. Easy peasy. Thanks to Tim Berners-Lee, we can throw a select dialog somewhere. And then we'll add an end condition to our query, and we can do created at now from the last week. Amazing, our users are happy. But then this one comes around. Users can find long lost to-dos based on arbitrary text queries. Okay, we'll throw up a we'll throw up a search box. That's great. But then we're going to land on it depends. And this is that time where you break out your question mark agile poker card, because this could be anything, and it could be pretty complicated. And obligatory XKCD, although this was from 2014, and I don't know where the time has gone. And it's a bit wild that the example from this actual comic is actually an afternoon's worth of work now. So yeah, congrats us as an industry. We've made things easier. But yeah, we're going to spend the next 111 slides qualifying why it depends. So yeah, welcome to my talk. We're going to cover 3 approaches to search. We're going to do substring matching, full text search, and vector search. And the approach we're going to take is kind of focused on what the user needs, what the options we have to fulfill that need, and then I'll cover some tools that are available. Although crucially, I'm not here to sell you on a particular tool. I just want you to be armed with knowledge of what's possible, so that the next time you run into a similar problem, you kind of know what's available. You know what to put into Google. You can ask the right questions, and you know what trade-offs you're making, rather than like anyway. I'll get to like why that's important a bit. What this is not, like I said, I'm not going to dive into implementation details. First of all, I'm not an expert on implementing search engines, despite working for a company that is one. And it's a very deep rabbit hole that I have some context on, but I'm not going to go into. I'm here to solve user problems. And secondly, I'm not here to pitch you on a specific tool. Like I said, the best tool is probably the one you already have. Yeah, use what works. Why should you care? Text search is everywhere, and your users expect it to work. And for many categories of applications, it is considered table stakes. Here's an extract from a UX audit that Baymar did on top e-commerce sites. And I won't read it. I don't read it to you, as you're probably doing that right now. But basically, bad search experiences can lead to less money. And as if you're pitching this to your business, that's a pretty compelling. Pitch. Also, hi. My name is David Cornu. The hardest part of talking at this conference was writing my bio, so I really don't like talking about myself. But in the interest of lending some credibility to this talk, you should know that I was the custodian of search functionality on Shopify storefronts, which was part of kicking off a almost decade-long now effort to bring it into the 21st century. So a bit of context there. Also, I work at turbopuffer, where we provide vector and full text search on top of object storage. You may not have heard of us, but if you use Notion Cursor or Linea, we have moved your bytes. Small disclaimer, turbopuffer is not paying me to be here. I applied for this conference before I got a job there, so not here to sell you anything, but yeah, take that as you will. So yeah, the first technique I'm going to cover is substring matching, which is basically very common in like auto-completion, type ahead style experiences like incremental search. And it's usually, at least from experience, the first thing that gets added to an app. Typically in like an admin dashboard, you need to find an organization or a user by name, and you don't really want to, you know, scroll through a list of 20,000 entries. It's much easier to just like type the name that you already know. These sorts, is this going to work? Yay! These sorts of interactions are everywhere, and they help you quickly narrow down, you know, a potentially huge list of something you're familiar with. So that was an example from GitHub. Here's another example from the settings dialog on macOS. But you know, you might not know where the accessibility settings in, so you'll put something in the text box, and based on the contents of that string, we'll find things that match that. And so even though you might not know like where in this complicated like hierarchy like the right setting is, like you get to access it pretty quickly. Here's another example from, I don't remember what this is called anymore, but it's like, anyway. But yes, sorry. This is Raycast, but yeah, Spotlight does the same thing. But yeah, you can, oh yeah, it's really nice. I use this every day, and I don't know what it's called. But yeah, you want to look for Firefox, you type FI. Why is Firefox the first result? Well, it's a string and it contains FI, so that's probably what you wanted. So yeah, very useful in cases where you kind of know like you know what to type. Conceptually, this is quite simple. This is a Rails-ish looking thing, but this is everywhere. Given an input, we narrow down results to the ones that start with that input or could contain it as well. If we want to minimize data across the wire, save on memory, deserialization overhead, or simplify our implementation, we can often get away with doing this in the database as well. So we have a big table with a bunch of, I think these are to-dos. So like if I type G, we can narrow this down very quickly to the results that we want. The tool of the trade here is like queries and their friends. So like queries are in most like RDB relational databases. There are equivalents, like you can use regex and MongoDB. And basically, there's an example of what a query might look like. But basically, you get a % as a wildcard. And so if you're looking for things that start with G, you could do G%, and you're off to the races. Some considerations, though, and like this talk is basically all weird things about text that you should take, like think about when you're implementing some of this. So I guess first consideration, case sensitivity. So yeah, uppercase, lowercase m, not the same bytes. If I'm doing a like string contains other string, if the user types uppercase m, I'm not going to give them the same list of results. So this is something that you need to take care of. There's two ways to take, like there's two ways, oh, I should mute myself so I'm not hearing myself from my laptop. Yeah, two approaches. If you're doing it in memory, you can do pre-processing. This could be as simple as like, this is an example from Ruby, but all languages that we use will have a way to do this. If you're using regexes, like you can do like /i flag for case sensitivity. And you can use ICU collators. I'm specifically not going to talk about that because I'm going to get to it in a second, but it's a solution here. On the database side, there's ilike in Postgres, which is case insensitive like. You could store your data in lowercase. CI text in Postgres does this for you. You don't have to care. It just lowercases and stores it. And so then you like it just happens in the background. And we're talking about collations again, but we'll get to that in a second. Another consideration, and this is something we're very familiar with in Montreal, but less so when with my US colleagues, is Montreal versus Montreal. Looks familiar. Again, not the same bytes on disk, but we probably want the one with the accent to show up in like a result if I didn't include it in the text string. Again, like two approaches to solving this. If you're doing this in memory, like again, example from Ruby, but there's actually you can use UniDecode in Python, or there's tons of libraries that do this. But basically, have some sort of a routine that takes accented characters and turns them into the ASCII equivalents. That way, when you're searching, you can only deal with like ASCII style characters. We're talking about collators again. Get to that in a second. On the database side, pre-processing. So Postgres has an accent extension, so you can call that as you're storing your data. Again, we're talking about collations. Told you I would get to it. So what the heck is a collation? In French, it's a collation. That's what my daughter asks for me 3 times a day. That is not what I'm talking about. So collations are sorting rules, and they're sorting rules for humans because if you have a set of strings, you could sort them by bytes. But humans don't think in bytes, and there's all sorts of like weird rules around like what comes first. Again, if you're only used to dealing with English, like English mostly works with like ASCII ordering, say for like uppercasing. So maybe this is something you haven't thought of a lot, but if you're coming from like other languages have like pretty important rules around this. Here's an example from, so this is the I can't remember which Unicode document this is, TR10, but they give a good example here where like depending on the language, like the exact same character may come before or after. This is really tiny, but like O with the 2 dots comes after the Z in Swedish, but in German it's the other way around. And so if I'm a German user and I'm scrolling through a list of names that you've sorted what you think is the correct order, I might not find what I'm looking for because it won't be at the correct spot. This is, yes, so like this is all the kind of thing that we can rely on the Unicode Consortium to do, which is great. And this is very important work that most people have never heard of, except for when they release new emoji, which is a great way to get people to upgrade their Unicode versions. So as an example, like if you're dealing with databases, we'll take like MySQL's default, like what's a collation. So UTF-8 is the encoding format. MB4 is up to 4 bytes per code point. Again, you shouldn't have to care of this, but some of us in this room have lost a lot of hours to this crap. When it only stored 3 characters and emoji was introduced. We can talk about that afterwards. 0900 is, so like I was saying, the big document over there has been versioned over time. This is the version 9, which is from 2022, I want to say. And then the important bits are the AI and CI, which is accent insensitive and case insensitive, which means like when we sort, say we're storing names in the database and we sort the names where if there's an accent or if there's an uppercase, those will get considered to be equal. So like as part of their work, Unicode vends several libraries. You've probably heard of ICU, probably because you installed Ubuntu and it's complaining that the locale data is not available and you don't care, you just want to deploy your app, but it is important. They also, so the examples I'm going to be giving are from ICU for X, which is a newer library that they released in Rust, and the idea is this can act as a common base for a bunch of languages. But here's, I don't know if that's big enough, but basically what I'm showing is that I take an uppercase Montreal with an accent and all lowercase, and depending on the settings that I give the collator, in this first example, they're equal, despite being different bytes. And in the second one, if I go to a more strict mode, they're like the first one is greater than the second one. All this to say, these are algorithms based on human rules that are published that we can use. So another consideration, normalization. Again, one we're probably more familiar with in Quebec than in other places, but if I'm writing A can be one of 2 formats in bytes. You can have the canonical, so U plus 00E9, that's the canonical accent aigu, but I can also write it as Latin small letter E with a combining acute accent, and like there's a lot of combining characters even for emojis, and so oftentimes these are technically the same, like the term is like grapheme, but the bytes on disk are different. This is how you get Zalgo for the children of the 90s. But basically, Zalgo is like, let me take these normal letters and like show a bunch of stuff on top, and you can combine them basically infinitely, which is great for flexibility, kind of annoying if you're trying to compare characters. So solutions to this, in memory, you probably have to think about like, so in Ruby there's Unicode normalize, but like in other languages there's equivalence, and you can basically apply that to your strings to make sure that they're all at the same format, so then when you're comparing them, there's equivalence. And like I said, there's ICU libraries are available in a bunch of languages to apply the same transformations. On the database side, this is thankfully something we don't have to care about, because I think, well, depending on how you configure things, but like for example, MySQL by default is accent and like uppercase, lowercase, like unaware, because the default collation, like we saw, takes that into consideration. These are the kind of things that you don't really think about, like Unicode normalization, until like a real problem. This is an example of it biting a lot of people in the ass, like semi-recently, when Apple did the HFS, which was normalized, to APFS, which was non-normalized. All of a sudden, files that seemed to be the same file name were no longer the same file name, and this caused like a pretty major kerfuffle in the Apple developer community. So it's a problem. It's worth knowing about in case it bites you one day, and then you'll know this is why it's the case. Yeah, same example from the library. You'll see like the second statement there, where like I'm showing you that it's equal. This is basically taking the default collator for English, and I'm comparing eacute, the 2 different ways to write it, and you'll see that when I do compare them, they're equal. Okay, another consideration is user behavior. So I'll keep repeating this throughout the talk, but when it comes to search, because the answers aren't necessarily like, you're trying to solve a user need, you're not trying to like answer an absolute truth. Having a test corpus and like having representative queries and like kind of keeping track of what your users are actually doing will help you deliver a better experience. And often this isn't like the most obvious thing. So I'll give you an example. Those of you who've used like Rustdoc, one of the things they support is aliases. And so, for example, if I come from Ruby and I'm looking for, so Ruby calls reduce inject for reasons I don't understand. But anyway, if you're writing a ton of Ruby and you switch to Rust and you look for inject, you're not going to find it because it doesn't exist. But like, because of that, they added inject as an alias for iterated unfold, so that if you happen to type this in, you're going to find the right results. Same applies to a lot of search experiences where you're going to notice that your users are typing support into your like search box. Like you should have a result for that because like they're doing that because they don't know where else to go. And so those are cases where you can help them have a much better experiences. But like knowing that is very much based on observing users in the wild. Sorry, Andy.
By the way, it's called inject as well in Ruby because sometimes you're thinking of an array. You want to inject each one of the elements into a block to process it. That's what they call it, inject. So depending on your needs, if you're reducing an array into one value, you just use it as reduce. If you're focusing on the injection, then you call it inject.
Today I learned. All right. So like still more considerations. So performance. This really comes down to like how many strings are you actually looking through. From experience, like so things that are bound by the real world, like for example, if I'm searching through like email contacts, you're just not going to have 100,000 email contacts unless you're like really messing with the system. So things tend to have natural limits, and like scanning through those is relatively cheap on modern hardware. And so there's often a lot more gains to be had to just taking your total result set, narrowing it down to like I guess current user or the current organization, or depending on your app, and like actually scanning through that. In general, you'll find like a lot more gains that way. This is a very well-trodden path. If you want to look at some in-memory implementations like FZF and KBAR in the React space, have interesting implementations, and like, yeah, there's nothing new for me to share here, but those are interesting repos to look at. Also, don't underestimate how far like in-memory approaches can take you, especially with like stream matching. So it's probably not clear from this, but like if you've used that mentions on GitHub, what GitHub does is they basically take all the contributors or everyone that's participated on a repo, and then like if you type @ into a field, they just shove it down to the browser, and then you are doing that searching like in memory on your browser. This is also why you can't find new hires on GitHub, because they just they're not part of that list. But yeah, so this was for my example on like the Linux repo, it just sends you 17,000 usernames. It's just like, here, you search them. And this works fine. I mean, no one's complaining that like GitHub's @ mentions are slow. I have complained that I can't find new hires, but and yeah, there are extremely fast ways of doing like substring search. If you're curious about this topic at all, Andrew Gallant, who's a member of the Rust community, who goes by Burnt Sushi, has a terrific blog. He's the author of ripgrep, which you might have used as a command line like searching tool, but he goes into like extreme detail as to like how do you optimize these kind of use cases. If you do actually need to search through like substantial amount of strings though, so like at work we have this use case where if you create like, it's our version of a bucket, we call it a namespace, but we have like millions of namespaces and they're identified by their name. And so yeah, we do actually, like if a user is coming in and wants to like find their specific, like a specific one, like we need to actually search through a whole bunch of strings. The good thing is most databases can use regular old indexes to do prefix matching. So if I'm searching for MONTR as opposed to like %, as opposed to like having a % before, you can scan through a B tree and start at MONTR and just go forward. And this is a very quick operation. And so if that's your use case, that works super well. And yeah, if you're using, you can deal with like accent sensitivity and case sensitivity through collations. Although in researching this talk, I realized this is not like, we do this in MySQL, but like support in Postgres landed in 18. So before that, you had to do some pre-processing. But yeah, do some research if you're running into this. And if you're doing prefix search, like it's a pretty straightforward solution, and you can just use the tools you already have. Here's an example of doing that. So from Postgres, so like create a collation I'm using, so like the French example. The naming is basically, it's like I'm using an ICU collation, and the weird string is basically French. We're using a Unicode collation, and the key sensitivity level basically determines like case and accent sensitivity, basically, but level 1 is what I wanted. I inserted a dictionary worth of words that I got from the LibreOffice project, so it's like 40K words. And then if I query être with a capital E and no accent, I'm getting correct results. And if I look at the explain, I'm doing an index-only scan because it's able to reuse the B tree for that. I'm getting to that. But if you're doing like an autocomplete style thing, usually this is a lot more straightforward than using full text search. I will get to why this slide is really long and I can't see my notes. All right, then, yeah, so what if you absolutely need to search by substring on a huge corpus of text? So like you're not doing prefix, you're just doing like, find me this like string within like a longer string. The classical example of this is code and regex search. So if you've used GitHub code search, that's basically what they're doing behind the scenes. And the strategy here is what's known as n-grams. So I've given you 2 examples here. Basically, if it's a 3, it's trigrams. If it's 2, it's bigrams. There's different names for them. But basically, the idea is you take the contents of your string and you split it up into, in the case of trigrams, into like 3-letter combinations. And that gives you a whole bunch of substrings that you can index. And like, I'll get to how in a second. But basically, you can take your input. So if I'm looking for MONTR, I can take my input, find the same trigrams within my input, and then find entries in my database that have those same subsets of strings in order to like find a match for the user. And let me make sure I covered. Yes. Why won't this fit? Anyway, problems. So yeah, here's an example from Postgres. There's an extension for this called PG trigram. If I show you, so like here I'm just showing you like what you get from Montreal. It adds a couple spaces at the beginning so that like basically treats every word as like starting with 2 spaces and ending with 1 space. The idea behind that is it will weigh word boundaries higher than the middle of the word, which is probably what you're looking for as a user. You can create an index for that. So it supports, this is like using Postgres' GIN indexing. And you'll see that like when so if I didn't explain here, but basically what it's able to do when I look for constitut in my list of French words, it's able to do a bitmap scan, which narrows it down to 8 words. And then it does a recheck for things like casing and things like that. But basically, I'm able to do an index scan to find a smaller string in the middle of a longer string. The big advantage of this is that, so here's my entire French dictionary, and I've narrowed it down to 10K entries. So that's relatively cheap to index, and it's not going to grow exponentially because this is the whole French language in theory. So yeah, this number is going to stay relatively bounded, and that there's only so many like 3-letter combinations, and so it becomes a lot more efficient to kind of do these searches. Yes. There was a super interesting write-up as like, so because this seems like a very simple technique, but this technique was used to power Google. Well, those of you who remember Google Code had a really cool search functionality, and there's a terrific series of blog posts as to like how they implemented that. But the crux of it is they let you do like a regular expression search, and they basically took the long strings within your regular expression, did a trigram search, and then reprocessed that. But we're able to like search immense code bases and like everything that they hosted to find like the specific string you were looking for like super efficiently. And the same thing inspired GitHub years later, where they're using the exact same technique to basically index all the code on GitHub. When I talked about, so like the trigram example, you might have said, okay, but wait, I'm taking one word and now I have like 6 different entries. Like what gives? Like how are we indexing this? And like in theory, we could have like an n-grams table, and like that would probably be fine. There's a much more efficient way of doing things, and you'll see this in like basically once we start talking about like full text search within Postgres or like in other search engines. Typically, they'll have a data structure called a posting list. There's different, and it's also called like an inverted index. And like basically, this is a much more efficient way to store things like n-grams or things like subsets of words in a way where we're able to like quickly determine like which documents have which which documents are these entries are contained in. So like when I did my create index, you saw, oh, we're using GIN. Well, GIN stands for generalized inverted index, which is a feature of Postgres where that's how all the like their full text and like n-gram functionality works. I won't go into too many details, and this is really tiny, so I guess I'll talk through it. But I wanted to give you an example as to like why these formats are more efficient. So like one of the formats that like search engines use for storing an inverted index is called a bitset. A bitset, if you think about it, is a like a long array of bits. You give each of your documents an ID, and that ID corresponds to an offset in this long bit array. And you basically flip the bit for if it does contain that document. So that means you can basically like load these and quickly determine like, okay, if I'm looking for MON, I know that document 1 and document 101 have that entry. If I'm looking for TRE, I know that document 1 and nothing else have that entry. And the big benefit here, this sounds like horribly inefficient, but this compresses super well because you have a lot of zeros. And like usually search engines will optimize like terms that are rarer first, so you'll narrow down your set of documents pretty quickly. And the other thing is like, because this is like a columnar format, basically we're storing the value of MON for that specific document, but like all together, like CPUs are quite good at scanning through like long linear things. And so this ends up being significantly more performant than like scanning through a B tree in a relations database. So to recap, some considerations for substring matching. We talked through normalization, accents. This is called ASCII folding in other places if you're looking at documentation, and case sensitivity and approaches. So yeah, like don't knock like in memory. That works quite well. You can index like prefix likes with just like regular old indexes, and you can consider n-grams with an inverted index for like more complex use cases. I'm going to drink some water now because my throat is going to die. All right. The second technique I wanted to touch on is what's known as full text search. And so to give you kind of an illustration of what that means, we're taking queries where in the first example, I might be looking for a tag or a name that I know. Like in my like Spotlight example, I typed Firefox because I knew Firefox existed. In full text search, we're taking user queries where they don't know the name of the thing they're looking for. They're looking for a document. And so it's not a given that like a document containing like 3-meter like USB-C to A cable is like going to be the right answer, or that like there will be a document with that. And these like as a mental model is like things you would type into Google basically. Yes, and yeah, like result as opposed to like substring matching. So like in the case of like in a substring, like if I give you like find this string within this other document, there's a yes or no answer as to like whether that's the case. In full text search, everything is an approximation, and so you're trying to find things that are relevant to the user's query, but like there's no like there's no like truth. Like it's basically trying to match the user's need. So I'm going to talk. So we're going to do something to walk you through kind of like I guess the mental model as to like how this works. I'm going to introduce this concept called terms. And so we're going to do something quite similar to what we did with trigrams in the previous slide. And so we're going to take, this is like the first paragraph of the Wikipedia article on jazz. I don't know, I don't particularly like jazz, but it was in my other example and end up working with these things. So we're going to talk about this paragraph a lot. But yeah, we'll take that paragraph, we'll split on word boundaries. So basically, instead of doing n-grams, we're going to split on like spaces in this case. And then we're going to store this same way we stored n-grams in an inverted index. That way we can quickly find documents that contain these words. And yeah, like I said, in full text search, these are called terms. I talked about like splitting on white space just to like let you know that like text is complicated. But like wei, which is like I am David in Mandarin, where's the space? Like white space isn't going to save you there. So like yeah, it's fine in English and it's fine in other thing in French, for example. But like this is a complicated thing. Fun aside, text coding is far from a solved problem. There's even a word for it called mojibake in Japanese. And people actually learned to like recognize encoding issues to like fix their documents. So we're doing great as an industry. So back to the topic at hand. So actually splitting on word boundaries is something that like Unicode thankfully takes the burden off of us. So this is an example of the segmenter from ICU4X, the library that they give us. You'll note that like, I don't know if it's clear from here, but they basically have like a machine learning model to split words in like low RAM environments, because like the other strategy is to basically ship a dictionary, which like is kind of wild, but like, yeah, humans are complicated. So we'll take our tokens, we're doing some processing on them. Same thing as like the substring case, we have mixed casing in here. So we're gonna do the same thing in like lowercase everything. We're also gonna remove, there aren't any accents in my example, but you can imagine. So we're gonna move the accents as well. And then we have all these words that aren't that meaningful in English. These are known as stop words. And so most search engines will just like get rid of them. They're not really worth indexing, they're just noise at that point. And so for example, if you're using OpenSearch or Elasticsearch, they come with a built-in dictionary for things you want to probably get rid of. And so yeah, and I'm not searching for those, so I can drop those out. And then we get to more like advanced cases. So for example, if we look at these words, like originated, communities, early, centuries, like in the document itself, that's a plural. But if I search for like century or community, like singular, I might want to actually like get results for this document. And the strategy that's used here is like algorithms called stemmers. And so stemmers take common forms of like words for a language and then transform them into common stems so that both the plural and the singular turn into the same kind of underlying token. And that helps you match for these kinds of cases. This is an example. So Porter 2 is a very common algorithm for English. But basically, if you look at Snowball, like Snowball is a collection of these stemming algorithms for different languages. And these are basically based on like linguistics research to find good ways to like represent similar meaning words and like, or similar rooted words with the same string. If I show you what that looks like, you saw like genre became, I don't actually have a good mental model for why like genre became that, but origin, community, early, century, that makes sense. And it doesn't matter that these are not real words. It matters that the same, like multiple words will end up looking like this, put through the same algorithm. And so that lets us handle, so yeah, like if I type earlier or early, I'm still going to get the same result because I'll take the user's input, put it through the same stemming algorithm, and then I can find these matches in my database. Another thing you might want to do is so named entity recognition. This is a whole area of research, but basically there are things in this paragraph that are like concepts, and you might want to extract those out to like give those more weight. For example, like if I type jazz and I know like that's an entity, like, or like if I type the name of someone, then there's an opportunity there to like give more weight to that token. So this is a whole area of research, but if you're looking into this, there's a lot of models that do this exactly. So this is a very simple model, but this is a customized version of Google's BERT. But like the only thing I wanted to get across is like you feed it my paragraph, and it basically determined that like, oh, African American is a concept, and like I can't remember what, like New Orleans I think is a concept below, but basically it's able to take that string and figure out, okay, these are the named entities within this. This is not the only solution. Like if you're dealing with a very like constrained problem space, like I don't know, you work for Best Buy, you could just like hard code a dictionary of these, like, oh, like I don't know, like brands, for example, or yeah, like certain like technical aspects. Like you're going to see that term a lot, so you can just like identify it early. Similar sort of issue. Synonyms. If I'm looking for a genre, I might search for like kind or style, and like if I'm looking for black music, like, well, am I going to type African American? Probably not. A common approach to this is to basically have like a dictionary again. So, for example, like if people are typing laptop, you might just want to convert it into computer. There's two general approaches. Either you convert all the synonyms to the same word. That way, regardless of the query, they end up being expressed the same. Or you append the synonyms to the end of your tokens and index those as well. Other things to bear in mind. If people are putting emoji in the text, you might want to convert that to upside down face, because I don't know that people are typing in emojis in search boxes. This depends on your use case. If you're indexing like web pages, like you might want to remove like HTML tags. You might want to unescape things. You might want to like decode formats like Unicode, where like the actual string that you're searching is not the string that someone would type that corresponds to that. Same for like I worked in e-commerce for a while, so colors and dimensions very important. But like if one like listing is in feet and the other is in meters, like maybe you recognize that and like treat it as the same. Like different, like these will all depend on like your use case. Yeah, all these techniques together are what's called like text analysis, which is basically taking your input text and then generating a set of tokens from it. And like how you configure this is very dependent on the specific text you're looking to index. But generally, like you're looking to customize this based on, like if I'm indexing a bunch of like English text, then maybe I'm going to use like the Porter stemmer, and then maybe I'm going to like stem using like anyway, different techniques for different texts. The next thing I want to talk about is ranking. So we saw this in the n-gram case, where in n-grams we're looking for a substring. So when I showed you the explain, it found the documents with those n-grams and then a rescan to figure out, is it the right combination, the right order? Does it actually match the query? In the case of like text search, for example, like that term might appear like many times, one time. These are all like in theory matching documents. Like if I search for jazz, I took the like first paragraph of jazz and then the first like paragraph of blues. like these are both technically matching documents, but one might be more relevant to the user's query. And so this is where like ranking algorithms come in. Well, actually, the first thing I'll talk about is the weights. So when we rank, so for example, if I go back to this slide, like if the title is jazz and you're looking for jazz, just give me the jazz document. That seems like intuitive, but like if I'm treating these as equal, then I might not surface that document first. And so typically when you're indexing your strings, here's an example from Postgres. It's very common practice to set different weights to different properties of your document. So like the name or the title might be several times more important than the parts of the body. That's just one easy way to get more relevant results. The other thing you'll hear about is ranking functions. So the most common one that I've dealt with is BM25. These all have weird names, but effectively, like if I talk through like what BM25 takes into consideration. So one is term frequency. So if a document says jazz like 15 times, like maybe it's more important. And but if it says it like 1,000,000 times, maybe not, like it's trying to spam, so there's like a configurable limit there. Inverse document frequency means like if in my entire corpus you type jazz and there's one document with jazz, like that document should definitely be the most important. But if it's like a very common term, then maybe you like don't take that into consideration as much. And then document size is one innovation in BM25, which is if I have a very short document that has like one token, like if I'm indexing tweets and you're talking about jazz, then like maybe that tweet is like more important than like 6 paragraphs where like jazz is featured once. Again, this is all guesses as to what might be relevant to the user, but like for example, BM25, like if you look at the papers for it, they're like, well, we tried a bunch of different stuff, and like this one seems really good. It's like cool, and like that is actually played out in like a bunch of implementations. But like again, we're trying to use like the information we have to try and guess at like what's important for the user. And so to bring it all together, like your indexing pipeline looks a bit like something like this. So take a document, run it through text analysis, you get your terms out, and then you put them into an inverted index. And when you come to query time, the important bit is that you're basically putting your query through the exact same analysis as your document. And so you get the same terms out. You then look it up in your inverted index that will tell you which documents have those terms. And then you will rank them based on like the term frequency, et cetera. And you will get an ordered list of terms. If you want to know more about this, there's a terrific talk by Erin McKean, who is one of the people behind WordNik, where she basically goes through like specific examples with specific words and like how to tune Elasticsearch to give good results. So if you want to hear more about that, I highly recommend this talk. A bit old now, but the content is all relevant. So yeah, some additional considerations. Your choice of text analysis will depend on your use case. So like, for example, if people are searching for categories, collections, tags, like those are going to be very short strings. Like you can maybe put those on n-grams. You also might you don't necessarily need to put everything into one index. So like, here's an example of H&M. Like I have related pages. Like if I typed RE, there's like returns, but I'm also being suggested like product suggestions, and those might be 2 different indexes that you just like query at the same time, and you'll get different results. But depending on your use case, like that might be the right approach. I'll give a brief mention to pre-languages. So like if you're an advanced like GitHub search user or an advanced like Google search user, you'll know that like there's ways for you to express constraints on the query. A common one is like, instead of like typically like we'll treat like a search query as like if you type like foo bar, we'll assume you want foo and bar in your results, but you can do like or. These are basically small programming languages. So Elasticsearch gives you one out of the box if you want to offer this kind of functionality. But I will warn you, because I lived through this, exposing these things and like by accident means your users will depend on it, and then you're stuck supporting it forever. Yeah. So really powerful tool. Use with care because you're committing yourself to support. And yeah, some tools you can use. For going from left to right is like based on pain. So on the left, there's solutions where like do it in memory, or like PageFind is really cool, where it'll basically build an index of what you want, put it into like a compressed like binary format, and you can just like ship that to the browser. And so you don't really need infrastructure for that. You can build the index on CI. Use your database, like Postgres, MySQL have full text options. MongoDB through their Atlas offering has also like full text options.
The latest release edition now, MongoDB also has full text.
Amazing. So yeah, then there's turnkey solutions like Algolia and TypeSense, or more specific tools like Redis now has like full text search. But and then if you want to go really intense, there's like toolkits like Lucene and Tantivy that will let you do that analysis and build your own like search query. Quick recap: analysis turns the document into terms. We index those terms in an inverted index. At query time, we do the same analysis to the query. And we find documents that share the same terms, and we can rank matches based on various stats. All right, I have 5 minutes to cover my last technique, so I'll be quick. Semantic search. So it's a bit different from full text, where in the full text we're finding matches based on like keywords or terms. In the semantic use case, we're trying to like find matches by meaning, which is a bit vague, but this is a very cool area, and there's a ton of active research going on. I'll give you an example. So like if you ask Perplexity a question, like it'll give you relevant results, but it's not like you're finding substrings or finding like terms in there. It's like literally answering your questions. Another example, like a bit smaller scale from linear. Like if you create an issue in linear, like it'll find similar issues for you. Like, is that because they have similar words? No, it's because they have a similar vibe. But then, how do we do that? So this gets us to the tool of the trade, which is vector embeddings. So vector embeddings are a type of machine learning model that take inputs and then give you a big array of floats, integers, whatever, but basically a big array of numbers. You can think of these as like coordinates in a multi-dimensional space, but like fundamentally what we're trying to do is put common concepts close to each other. The idea being that like, if I have a bunch of content around plants and then the user types a type of plant, I know that like that query is in this region of my documents, and so I can pull the stuff that's around it to answer their query. My mental model is, I don't know if you've ever had a workshop, you just throw stuff where like it was last used, and like you can find everything everywhere because like it just matches your thinking. And so until like someone cleans it up and you're totally lost, but like things that go together kind of end up together, and you can kind of find things in this like 3D space without like thinking too hard about it. Or a different example, like Pandora spent a lot of money and a lot of time like before these kinds of strategies were around, basically coming up with a categorization system that had like hundreds of like different like factors, and hiring musicians to basically categorize music so they could build a recommender system. Like this is what we're training these models to do basically, except we have no idea what the axes are. We're just getting a long list of numbers out. If you're familiar with Every Noise, is a great website by someone who used to work at Spotify. Like this is kind of what we're after. Like this person like basically spent a whole bunch of time like mapping every genre that Spotify knew about, and like it's like colors and vibes and similarity, but like you can find a ton of music there, and it's a good way to lose an afternoon. But like that's kind of what we're doing. But David, you said, isn't this all just hype? So wait, so 1 second. So as a demo for this, I put my French dictionary through that I was using in my Postgres examples. I put it through Embedding Gemma. Embedding Gemma is a open weights model from Google, so you can run it on your laptop if you want. And I put this into turbopuffer where I work because it's free, and that seemed easier. But if I query for winter activities, these are the results I'm getting. And I'm getting stuff that's super relevant, but like all I did was feed my query into like a black box, and now I can like return you 20 things that are probably related. Obviously there's some like noise in there, but like there's no way I would have found these with like a full text approach. Like this just straight up wouldn't work. If I query for plants, same thing. Like these are all plant-like things, but like and maybe as a user, like I didn't know that like I should look for a sapling, but like it's there, and like this is kind of incredible. The thing that's really wild is that if I type, like these models are multilingual, so if I type sport d'hiver, all of these words are like in English, but I can take a French query and return like relevant English results, which to me was just like a big, like I know how these things work, and like we have a ton of customers using this, but like seeing this in the like in a simplified example is kind of wild. And of course, you can index French words and do French like queries and get relevant results as well. So how do we use this? So you're going to see a similar pattern to what we're doing in full text, but this is like everyone tries different things. Like this is a very like throw shit at the wall kind of like area of computer science. Basically, like take a document, split it into chunks. The reason we do it with chunks is that like if you pass a whole document, it's unlikely that like for example, like if you have four paragraphs, like you'll get better results if like each of those paragraphs is indexed separately because it's probably covering like a different topic. So take chunks, pass them to an embedded model, so you get your big number. So you get your vectors out, and then you throw it in a vector database. And then you can get really fancy with this. So like an article from Anthropic where they basically take the chunk, ask a model, ask an LLM to like summarize where this chunk is in the document, and then add that text to the index as well. Again, throwing shit at the wall, it's great. And then when we take a user query, same sort of thing. We take the query, pass it through in a meta bubble, get a vector out. We do a lookup in the database, and then we basically rank them by, we do what's called an approximate nearest neighbor search. And we basically rank them based on distance to like our query vector. The reason these are approximate though is because in theory you could scan through like the complete list of vectors and get like an exact match, but that ends up being very costly in terms of memory because these vectors are huge. And so this is an active area of research, but basically we're trying to find ways to give you close enough results that like are more like 90% correct without like the memory cost and the like performance cost of like actually checking every one. We can talk about this after. There's hybrid strategies, so like they each have their strengths. So a lot of people just do both. Again, throw stuff away and like, but like you like in my example, you saw that like these things have different strengths, and so you can like throw your chunks into like text analysis and to an embedding model and get like both basically. And yeah, like when you do your query, you basically get two sets of results that you can then re-rank. If you want to get really fancy, there are actually models that do the re-ranking for you. So as an example, I took my search earlier and just searched for North American cities. This is like straight up like the model example. If I throw it through Cohere, like none of these are really, but I get like the first 10 results are bang on. And like this cost me one API call. So kind of wild that you can, but like, yeah, very common strategy. And then just to show you the extreme version of this is like, if you're building an Ask AI system, you give your query to an LLM, let the LLM do its own searching, so you throw that through your like hybrid search thing, and then you give the user a response. I'm not expecting you to build these, but like Notion Search, for example, like this is the kind of thing they're doing, and they'll send us like 60 queries, and then give the user like one response. How many slides do I have left? I think I have like 4 slides, so I think I should be. Yeah, this is a very this is like a very hot space, and there's like tons of new stuff coming on. There's probably 3 new companies that have launched since I like started this talk. But a lot of similarity to full text space. Like a lot of people are adding like vector functionality, so you'll see a lot of similar names there. There's a lot of like model providers. You've probably heard those names before. There's toolkits if you want to do like more customized versions. I talked about a llama, which lets you run these models locally. And then there's a whole class of vector databases where like are trying to optimize for that use case where you have like a lot of data to look up by vector, and so the different trade-offs, different solutions there. All right, to recap, that was a lot of talking. So yeah, substring search, good for narrowing down like good values. You can do in memory or like queries or regexes with or engrams. Full text search, more complex documents. You have to like there's some decisions to be made around like text analysis and indexing depending on like what you're actually working with. You can turn to database extensions or like search databases like OpenSearch or Elasticsearch. And then yeah, semantic and vector search, good for more complex documents or like vibes-based ranking, approximate meanings as opposed to like exact terms. And yeah, you can also turn to DB extensions, search like we're adding this as well. Like MongoDB has like a vector like solution these days as well, or to like dedicated vector databases, depending on what your needs are. I will leave you with this though. Search does not have like it's not like a true or false kind of thing. Like if I throw a where query in my like SQL database, like I'm gonna get a true set of results. Search really depends on what the users are looking for. And so like in all these solutions, if you're throwing out, or like if you're like the constant with all the like throwing different solutions at the wall is that like you have to understand like what good search means for your users. And that means having good test cases against known data so that if you make a change, you can see what the actual like difference is, but also like watching, well, doing user testing or just like having good like instrumentation for what your users are searching for. So you can iterate and improve, because fundamentally like you're trying to solve their need as opposed to like some arbitrary value of correctness. A shortcut could be to read up, if you're in the e-commerce space, like Baymard like produces terrific research where they do like audits and user testing on like most popular sites and like summarize like the best practices for you. If you're in other domains, like this is still relevant, but like very valuable resource. And that's it. Slides are there. I made it slightly over time. So I think, yeah, thanks a lot.